Okay, hello friends. I hope this mic audio is better than what I had going on the last 2 weeks. Um, that's it. That's the tweet. Okay. So today we will be covering. Oh, not that. We're covering linear inequalities in two variables. Okay. Very, very easy, and then you can do fun systems of equation stuff with it. Okay. So, one works almost exactly like linear equalities in two variables. Two, easiest to have in y r for like relation. So it could be like less or greater than, less than, greater than equal to, less than equal to, okay, mx plus b. So it can either be like y is greater, greater than, less than, greater than equal to, less than equal to, stuff like that. Okay. That's it. That is intrinsically the core of this. All right. Now, what is a solution? Solutions to a linear inequality are going to be ordered pairs that make the inequality true. Okay, same thing as with linear equalities. Yeah, so traditionally, right, you can have your solution as a set, right, like a set of blank comma blank, da 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 da, right? But if you have infinitely many solutions, as with most equalities and inequalities, you can just write it as the inequality, or it would be convenient to have as a graph. Okay, let's do a really fun example, and then you'll see kind of what I'm yapping about. Let's see. Suppose that you have y is equal to, let's do an equality first, 2x plus 1, right? The solution to this equality is going to be, let's see, 1 right here, 3 right here, and 5 right here, right? Solution to this guy will have your y-intercept here, you cross through like that, and it'll kind of shoot off into the distance like that, right? And this point right here is of course 0, 1, right? This point right here is going to be 1, 3, and this point right here is going to be 2, 5, right? Nothing crazy. If you want this point here, we can reverse engineer it. We know this is when x is equal to 0. Y is equal to 0. So you'll get 0 is equal to 2x plus 1. 2x is equal to negative 1. X is equal to negative 1 half. Negative 1 half, comma 0. Right? Great. And of course, because this is a line, right, it means these points and everything in between them is the solution to this equation. All right? Okay, now what if we extended the idea to an inequality, right? So suppose we have the same one, but the relationship is different. Let's do it in purple. So for example, you have y is less than 2x plus 1, right? Well, you know, right, that the boundary for the solution, right, is going to be, actually, it's going to be exactly this, right? And by that, I mean, let's see, we're going to shoot the line through like this. Off into the distance we go. We know that, let's do it in blue. You know that this is negative 1 half, comma 0. This is going to be 0, 1. let's say 3 lives here. This will be 1 comma 3, and let's say 5 lives here. This will be 2 comma 5, right? But that's not exactly what we're looking at, right? We want y to be strictly less than, right? And so what we actually want is we want to say, if I plug in 0 and 1, this inequality is no longer true, right? If you plug in 0 and 1, this is not true. But if you plug in all the points under, right, this inequality will suddenly be true. So the solution graph for this is not going to include this line we started with, right? Because dotted lines mean not included, right? It's just like with the one variable situation, right? Dotted line means not included. We want y to be less than, so we don't want stuff up here. We want stuff down here, right? And it doesn't just end here, right? We want stuff that goes like, just like that. So under your line. This is the solution set, okay? Okay, now what if we changed it up a little bit? What if we said, what if we want y to be, let's do in orange, less than or equal to, right? If you want less than or equal to, you will find, now what if you want less than or equal to, right? If you wanted less than or equal to, as we established, less than does cover this bit. It absolutely 100% does, right? But equal to also covers that line we initially drew, right? And so the solution for this is, oopsies, is not only the orange bit that we're about to fill in, right? Everything under. It also includes this line. So you want a solid line for that, all right? Okay, so we've done less than equal to. What if we wanted greater than, right? If we wanted greater than, oops. If we wanted greater than, let's do in yellow. If we wanted greater than, right? Well, we know that this solution set, this line, will make it equal. So we don't want that. We want it above, right? So we will go in, turn this once again into a dotted line, like that, and then fill above. Okay? That's greater than. Oh, but Amanda, what if we wanted greater than or equal to? I'm so glad you asked, because let's go in with green. No, I didn't do that right. What do we want greater than or equal to? Greater than or equal to. Here we are. We know this line makes it equal, right? All the points on this line are equal. And we want greater than. As we said earlier, greater than is up here. And that's it. That is your solution for greater than or equal to. It's actually pretty straightforward. You can also do this for nonlinear equations as well, but we'll get to that another time. Okay? Now, I'm sure you are simply dying to know what happens when I have a system of linear inequalities in two variables. Okay? So glad you asked. So glad. Another way to look at it is like an or statement, right? Let's do an example. And I'm gonna pause this. Sorry. You're like, oh, what if we want and alternatively or? What if we want a compound inequality? Again, stupid, silly, easy. You're not ready for this, okay? Let's find us a nice system to work with. Let's do one of them in green, okay? Let's say y is greater than 1/2 x plus 1. And the second one we have is, let's do pink actually. X plus y is less than 1. Sorry, positive 1. Okay? First, we want to, in y relation mx plus b form just so it's easier to work with, okay? So this guy I'm going to turn it into y is less than negative x plus 1, okay? Now we graph, okay? So y is greater than 1/2 x plus 1, okay? 1/2 x plus 1, let's say 1 is here, right? 1/2 x plus 1 means up 1 over 2, okay? So this point here is going to be x comma y, like that, right? And then we go up 1 over 2. So up 1 gives a coordinate of 1, over 2 gives a coordinate of 2, so 2 comma 1. And then we're going to go up 1 over 2 again. And that's going to be up 1 is 2, over 2 is 4. And let's do one more. Up 1 over 2. Up 1 gives you 3, over 2 gives you 6. And let's do one in the negative. Down 1 over 2, it's going to be here. And this is going to be, down 1 is 0, over 2 is negative 2, just like that. And then we can toss our line in, going this away, just like that, right? We want this to be greater than and not equal to, so we actually want this to be a dotted line. And to make it greater than, I'm going to go fill in this triangle. I'm not going to do the scribbles anymore just because it's going to be hard for you guys to see. So I'm actually going to fill it using transparent mode, just like that. Okay? So this is the solution to the first half. All right, now let's do the second half. We want y is less than negative x plus 1. Okay, we can do negative x plus 1. That means our intercept is going to be at 0, 1, just like here, right? It's going to be negative x, so it's going to be down 1 over 1, okay? So down 1 over 1, it's going to be 1, 0. I'm going to go down 1 over 1. This is going to be, x is going to be 2, y is going to be negative 1, down 1 over 1. This is going to be, x is equal to 3, y is equal to negative 2. Let's do one more. This is going to be 4, negative 3. Let's plug this back in and make sure I'm not lying to you. Negative 3 plus 1. Yep. And then let's go in this direction real quick. We're going to go like that, right? So it's going to be to the left 1, up 1. To the left 1, up 1 is going to be negative 1, 1. 2. I'm going to go like this. We're going to get negative 2, 3. We're going to go like this. We're going to get negative 3, 4. Right? Line looks okay. No weird business, no funny business. And then we're going to connect our dots, just like we did before. Probably should have done it a little bit differently in terms of placement, but it's a-okay. I'm going to actually shimmy my wood down a touch, just so we got some space. Alright. Okay, now if we go back to our line, we're going to see, oh, this has to be strictly less than, so it's this side. And we don't want a solid line, we want the dotted line, so we're going to go in, turn them into little dots or dashes. Doesn't really matter too much. I'm just going to make my dots in such a way that you can see the numbers under it. And you want this to be strictly less than, and less than is going to do something like this. I'll throw it in here. Come on. Oh, look at that. Brother. There we go. I'm going to turn it transparent. And there you have it. Oh, I forgot. Was this an and statement or an or statement? Let's say I want and, right? If I want and, then I want places where the green overlaps the pink, which is right here, right? It's not inclusive of the border because the pink doesn't include the border and neither does the green. And that is how you do the and statement. That is the graph of the and statement. But Amanda, what if you wanted or? If you want or, that's cool too. I'm gonna put our little colors back. Or means it's either pink. It can also be green. It does not have to be both. Oh, if it's an or statement in that way, it'll be like this. And of course, again, we don't include the boundary. And you're done. Oh, this is or. Okay. Pretty easy. So let me summarize this for you. 1, y is less than color under the line. 2, or similarly, y is greater than color over. Y is greater than or equal to, or less than equal to, include boundary. If strictly greater or less than, use dash to exclude boundary. 2, and statements require overlap of coloring, or statements require only one color, but of course both is okay. It's not exclusive or, that's called XOR with an X, X or, exclusive or. You guys need to know that. Oh, and the last thing, which I did not demonstrate for you guys explicitly, is when in doubt, that is, you're like, I'm pretty sure I colored it in right, but I'm not 100% sure. Choose one point in region that you want to check to make sure you did it right, and plug back into inequality to see. So for example, you're like, oh, I'm pretty sure I did this right, but I'm like not 100% absolutely positive. I'm gonna say, oh, okay, well, I'm pretty sure for my and statement, oh, here, already. That's the or, that's the solution for or. For my or statement, I'm like 97% sure that, the point 0, 10 is okay, but I'm not 100% sure. Okay, as long as it satisfies one of the statements, right, because it's an or statement, we're good. So we're going to plug in 0, 10 to the side. So check 0, 10. When x is 0, y is 10, 1/2, 0 plus 1. Nope, but that's okay because we have a second statement to check. X plus y is greater than 1, y is less than negative x plus 1. Okay. 10. Oh. Wait. I lied. This is okay. Let's check the other one just to see what happens. If I check the other one, I'm going to say, oh, when y is equal to 10, x is equal to 0, 10 is less than 1. That's not true, but it's okay because this is an or statement. Or requires only one side to be true. Okay, one equation. So this works out great. What if I want to check, let's say this guy. I'm pretty sure this region is okay, but I'm not 100% positive. Let's pick a number in here. I'm gonna go, this is gonna be negative, let's put it here, -2, comma 1. Pretty sure it's in there. I want to double check. And statement means both sides have to be true, so we'll check for both equations. We want to test -2, comma 1. I'm going to plug it into both equations, see what happens. When y is equal to 1, x is equal to -2, -1 plus 1, 1 is greater than 0. This is true. And statements need both. We're going to do the second side. 1 is less than -2 plus 1. 1 is less than 2 plus 1. 1 is less than 3. This is also true. So this region, perfect. Okay, that's it. Pretty straightforward. I do want you guys to work through some stuff, so please hold. Okay, for grade scope purposes, I want you guys to do number, and we're on page 79, 6 through 7. I also want 11 through 13. This is what they look, oh. No scrolling? Okay, that's fine. 11 through 13, they give you a graph and you kind of work it out. I want numbers 18 through 23. And I want 42 through 46 for our grade scope purposes, okay? I'm gonna make it a little bit harder. I also want numbers 56 through 59, okay? So this is a set of 3 inequalities, okay? Works similar to graphing 3 equations and, seeing what happens, all right? All right, thank you, friends. I will be back with more baloney sooner rather than later. Might start doing ASMR at this rate. All right, thank you, bye.